move on to the next little thing following this confidence interval formula that I've just shared with you. The formula, as I told you, consisted of adding and subtracting this number, which we usually call the maximal error. We did that for the mean thing weeks ago, and now we do it here. The thing is, we're going to turn it around to find, if we're going to think about how large a study should we do to be sufficiently certain about what we want to be certain about. We can turn this formula around. Can you see this? Blah, blah. Fast. You can isolate n here. Just move around on the other side and square and move around. And if you isolate n in this one, you get this formula. Telling you maybe something. Let's have a look at this formula. It's a sample size formula that tells you that if I have some kind of wish or requirement to the size of the maximal error, let's call that E. If I said, I want a maximal error when I do this experiment at this number, say, plus minus 1%, percentage thing, percentage point, percent point, what do you say in English? Percentage point, percentage value. I want that with a certain confidence. I should use the set, often the 1.96 from a 95% confidence. Then we have a problem. To find out how many voters or how many people, how many teachers should I ask if I want to be more certain about how many teachers really finds the problem. Is it really 1/3 or is it 2/3 or is it just 1/2 of the teachers? What is the real I wanted to know it more securely, right? More certainly. How large a study should I do to find out about that? Well, the problem of this formula is the following. That in the formula enters the P, that is the proportion of teachers that believes there is a problem. And I'm sitting now trying to plan, how should I do a study to find the P, the proportion of teachers that has a problem. I need to know the P to plan a study to find the P. Of course, you shoot yourself in the foot here. How could I do that? Well, you have to do a bit of that. Often it is with sample size considerations. You have to work scenario-based. That's kind of the only, not quite, but at least that's a good start. You could work scenario-based. You could use a guess, or you could say scenario-based for P. And then you can compute in, right? If you believe the percentage of teachers is around 50-50, how big should N then be to find a good precision here? Then you might be a bit off if P turns out to be slightly differently, but you could work scenario-based. Like this. In this case, actually, there is a nice little mathematical thing that you can use, even though it's a bit expensive, but if you have no information whatsoever, it's still a strong tool. Because if I plot the function f of x, that is x times 1 minus x, for p times 1 minus p, right? If you think about how this function is acting on the interval between 0 and 1, which are the valid values for p. This is a parabolic function going like this. Nice parabolic function here, with the top in 1/2, right? You could find out about this yourself, I know, based on tools you have learned in math back in high school, or just using some plotting function of Mabel or something, you could realize that this is the case. And what is the value of the function here? Well, that's 1/2 times 1/2. That is 1/4. So if I, instead of p times 1 minus p, which is the unknown p, if I put in 1/4, I know that all other possible values of this one would be smaller, right? So I'm on the safe side in terms of uncertainty. I put in the worst possible for the uncertainty. So the uncertainty must at least be smaller than that. So if I use that, I'm on the safe side. It can be expensive. but let's try. Let's try to plan a teacher study where, I mean, the standard error or the confidence interval was like 14 percentage points, right, in the study we had. That's much too big. Let's see, I'm going to be ambitious now. I want to have a maximal error of only 1 percentage point. Let's think about that at least, see what the consequence is. If you do polls for people voting, 1 percentage point is maybe a good thing to have such. I saw that. Okay, I'm back. It would be a valid thing to do. Let's try to compute the thing. And let's use this one. Actually, if the number of teachers were 50-50, this is the right formula to use. So we should compute n equal 1/4, 1.96. I should say that I use 95%, that is alpha equal 0.05, divided by the required number and squaring it, and let's see how many teachers we should actually ask, or how many voters we should ask to have such a precision in a poll. If the percentage would be around 50-50, right? If that's the percentage, this is the amount of people we should ask. Oh, I prepared this number already here. 1/4, 1 times 1.96 divided by 0.01 squared. Let's see what the number is. 9,604. This is actually a nice number for you to remember for the rest of your life. Let's say 10,000. To do polls with percentages around 50-50, if you want to be certain with a confidence interval on such a proportion, a certainty on 1 percentage point, and I mean proportions in percentage is something you are presented with every day if you read the newspaper, or read scientific journals, or do business in your company. You will meet proportions. It requires 10,000 observations, 10,000 observations to know a proportion in the middle of around 50%, to know it with a certainty of 1% with a confidence interval. It's even plus minus 1%. It's not even just an error. It's plus minus 1%, right? 10,000. So don't get too enthusiastic about polls based on a few hundred, right? It's not that they don't say anything. It's just that we should realize the uncertainty in this. But then again, the American thing with 10 millions is way beyond past. So that would have the percentage would have been extremely correct if the sampling had been correct. So, but often the sampling is a larger issue, actually. Question? Can you get a necessary number of samples that is higher than the actual population you want to look at? It's a good question. Can you get this number here, the required sample size, could that by chance be larger than the population size, the size of the population? And that's a two. If we are dealing with infinite populations, then the answer is no, because it's infinite. But many populations really are not infinite. And then if you use this formula, yes, you could. But then this is actually not the right formula to use. If we move on and sample big proportions of a population, we should go towards the hypergeometric distribution and use a formula based on that one instead. And then it would just hit the limit of the population at the end. But so that's a very nice question, but not a detail, not a subtlety I will enforce you to realize at a given day and some weeks. Okay, this was the third part. We have one more thing before a nice break.